bonds. What is a covalent bond? In a covalent bond, electrons are shared between non-metal atoms only. So it's only the nonmetals. You see them here in orange on the periodic table. Those are all of the nonmetals. They're mostly on the right side of the staircase on the periodic table, with the exception of hydrogen. That's the only one on the left side. Electrons here are going to be shared, just like in this example. You can see they're shared with a bond line connecting atoms together. This is a lot different than ionic bonds. When ionic bonds come together, they're taking away electrons or giving away electrons. Again, in covalent bonds, they are sharing electrons. When naming covalent compounds, we're going to use prefixes before the atom names. We have mono for one, two is di, three is tri, tetra, penta, hexa, hepta, octa, nona, and deca. To name a covalent compound, we're going to look at the subscript for each atom. That subscript will determine the prefix an atom will have. So in this example, we have P2O5. The subscripts are those tiny little numbers at the bottom, and those numbers are going to tell us what prefix to use for each atom. You also need to change the ending of the second element, change the ending of the name, using the shorthand form followed by "ide." So PTO5, for example, P is for phosphorus, and it has a little subscript 2. So we're going to look at the prefix chart. 2 is di. So we're going to call this one diphosphorus. And then we have O5. O is for oxygen, and 5 is a subscript. 5 is for penta. So that's going to be pentaoxygen. Now we're going to have to change this name, so that's not the official name. The first thing we're going to change is you see that A between the T and the O. That's too many vowels right there. So we're going to take away that A, and it's going to be pentoxygen. And then again, we do need to change that ending to "ide," only on the second word, not the first word. So instead of pentaoxygen, it should be written as pentoxide. Remember, if there is no subscript after an atom, imagine a 1 being there. For example, in CS2, C does not have a number after it. There's no number there. So we're just going to pretend that there's a 1 there. But another important rule to remember is not to use the prefix mono for the first element. So if you don't see a subscript for that first element, example here is C, we're not going to add mono for 1. Mono is only going to get added for the second element, never the first. So CS2, C is for carbon. Again, we don't use mono, so it's just going to stay carbon. S is for sulfur, and then there's a little 2 as a subscript. 2 is for di. So this is going to be disulfur. Once again, we need to change that ending. So instead of sulfur, it's sulfide. So we're going to call it carbon disulfide. All right, go ahead and name the following compounds. Push pause on the video and then hit play once you are done. Okay, let's go ahead and check our work. PBr5 should be phosphorus pentabromide. S4N2 should be tetrasulfur dinitride. SiI4 should be silicone tetraiodide. And PCl3 should be phosphorus trichloride. Remember to change all the endings for the second word to ide. IDE, IDE, IDE. Don't forget that part. When we're writing the formulas, going backwards now, there's no crisscross of charges like we would do for an ionic bond. We're going to simply write the symbol of the atom named. Then we're going to use the prefix to write the number for the subscript. And this time we are not going to reduce to the lowest terms. So whatever the numbers say, we're going to keep them as is. They don't cancel each other out. Carbon tetrachloride. Carbon on the periodic table is C. That's the symbol. There's no prefix in front of carbon, so it's just a C with no subscript. Then we have tetrachloride. Remember, this is a two-part word. The prefix tells you the number we're going to write after the symbol. So really we need to look at the periodic table for chloride. But again, don't forget that IDE was changed. So we need to look for the original form of chloride. Looking at our periodic table, we can see that chloride looks a lot like chlorine, and that's what it is. It's chlorine. We just changed it to chloride. So the symbol Cl, and then tetra on our prefix chart is for 4, so we're going to write a little 4 after that Cl. All right, go ahead and write the chemical formulas for these examples. Push pause on the video and hit play when you are done. Let's go ahead and check our work. Triphosphorus pentanitride should be P3N5. Boron trifluoride is BF3. And diarsenic pentoxide should have been As2O5. Now let's get to Lewis structures for covalent compounds. Let's review a couple of things before we actually start drawing the Lewis structures. First, valence electrons. Valence electrons are electrons on the outer ring of an atom. They are the most important part of the element. They are what's going to bond the atoms to other atoms. Recall that the number of valence electrons is indicated by the group number on the periodic table. Here we have the group numbers for each group below. Remember, groups are vertical, they go up and down, they are the columns on the periodic table. We can have more than 8 valence electrons, which we're going to talk about in a little bit. So, group 1 has 1, group 2 has 2. We skip transition metals, but once we get to group 13, we can't have more than 8, so we're just going to look at those last digits on the right side of the periodic table. So group 13 would have 3 valence electrons, group 14 will have 4, 15 will have 5. And these valence electrons are going to be the dots we're going to draw around our symbols for our elements. The only exception to this rule is helium. Helium is in group 18 because it's a noble gas, and all of these right here on the right side are noble gases. However, helium has an atomic number of 2. That means it can't have more than 2 electrons. So helium only has 2 valence electrons. The rest of the group has 8. So the octet rule. Atoms want to fulfill the octet rule, meaning they want to have 8 valence electrons on its outermost energy level. Atoms will form bonds with other atoms to fulfill this rule. The only exception to the octet rule should be hydrogen, which only needs 2 valence electrons. Since it only has 1 ring, it can't hold that many. And boron only needs 6 valence electrons. So we're going to keep that in mind once we're drawing out our Lewis structures and once we're checking our work. When drawing Lewis structures for covalent compounds, we will use dots to represent electrons and we will use lines to represent bonds, just like in this example here. Here we have carbon tetrafluoride. You can see they're connected with lines, and you can see extra valence electrons on the outer atoms. Each bond is going to represent a pair of electrons, or 2 electrons. Single bond will hold 2 electrons, double bonds will hold 4, and triple bonds will hold 6. Sometimes you are going to need to connect with more than one line. Not all the time, just sometimes. Polarity is going to be the distribution of electrical charge among the atoms in a chemical bond. Once we draw them out, we're going to be able to determine the polarity. Polarity is important because it tells us whether the electron cloud is equally distributed or whether an electronegative atom is affecting the electron density. The distribution of the electrons will affect the behavior and reactivity of the molecule. We have 2 types of polarity, nonpolar and polar. Nonpolar covalent bonds is when electrons are shared equally by the bonded atoms. This is going to result in a balanced distribution of charge. And since it's balanced, it's going to have a symmetrical electron density. We'll be able to see it when we don't see any lone pairs on the compound. We'll get to what that looks like in the examples. Then we have polar covalent bonds. This is our when electrons are more strongly attracted by one of the atoms in the bond, which gives an unequal distribution of electrons. This results in a positive and negative charged side, much like a magnet. Since they're different charges, we're going to have an asymmetrical density. And you will see this in our drawings when you see a lone pair on the central atom, which we'll talk about what that looks like here. So we have nonpolar on the left. Here we don't see any lone pairs. And on the right side, we have polar, and these are the lone pairs we're going to be talking about. We only care about them on the central atom, not on the outer atoms, but they're just a pair of electrons that aren't connected to any other atom or any bond. Let's draw out CO2. So when we look at CO2, we can see that there is only one carbon and two electrons. So when we draw this out, we're going to put the single atom in the middle, so carbon, and then we're going to draw two oxygens around it. Next, we're going to look at the periodic table to determine their valence electrons, so the number of dots we have around each one. Carbon is in group 14, so it's going to have 4 dots. 1, 2, 3, 4. Oxygen is in group 16, so it's going to have 6 dots. 1, 2, 3, 4, 5. Normally the sixth one would go here, but to connect the lines better, we're going to put the sixth one on the opposite side. We want the single electrons facing the middle so we can connect those dots together. All right, this oxygen also has 6. 1, 2, 3, 4, 5 at the top, and then I'm going to put the sixth one on the side again, so that way the single ones can be facing carbon. Now you're going to connect all the single dots together. So oxygen is going to connect its single dot. And then we still have another single dot here, so I'm going to connect that one as well. Same thing on my right side, single electrons are going to connect. And then I have a single dot here and a single dot there. So I'm going to draw this going around right here. This looks a little bit sloppy, so a cleaner version of this is going to look just like this. You won't always see the electrons that were being connected, so those pink dots in the middle are going to disappear, but this is an example of a double bond where 4 electrons are shared on each side. We call this example linear. This is the 3D geometric shape, so it's linear. And we also say that it's nonpolar because there are no extra electrons on carbon. Let's draw out our other example, F2. Here we can see we have 2 Fs. So I'm going to draw out 2 Fs. Since they're equal, they're both the same, doesn't really matter. We're just going to draw 2 Fs. Fluorine is in group 17 on the periodic table, so we're going to draw 7 electrons. 1, 2, 3, 4, 5. Again, I want these single ones facing the other fluorine, so I'm going to go backwards. 6 and 7. I'm going to do the same thing here. 1 on each side. 1, 2, 3, 4. Then I'm going to go back to the top. 5, 6. Bottom one's going to have 7. Now we need to connect those single dots. So this is what our example will look like. Those are the only single electrons we have. This is a cleaner version of it. We're going to also call this linear. It's also nonpolar because both of our fluorines are the same, so they're both equal to each other. Now let's do H2O. We have 2 hydrogens and 1 oxygen, so this time we're going to draw oxygen in the middle. And we're going to draw 2 hydrogens on the side. Hydrogen only has 1 valence electron, so we're going to have those facing oxygen. Oxygen is in group 16, so it's going to have 6. 1, 2, 3, 4, 5, and I don't want the double electron on the side, so I'm gonna put it at the bottom, 6. Okay, so now we're gonna connect the single electrons. So we're gonna connect the single electron on hydrogen to oxygen, single electron from hydrogen to oxygen. Now you can see that we have extra lone pairs on oxygen. We didn't have those on the last example, so this is how you can tell that the structure is different. This is called bent because of those lone pairs. It is polar, and this is the 3D structure of what bent will look like. Sometimes you'll see it bent without the lone pairs, sometimes you can see it bent with the lone pairs. Let's go ahead and draw BF3. Here we have one single B, and we have 3 fluorines. So we're going to put B in the middle, and we're going to draw 3 fluorines around it. So when drawing our dots, boron is on group 13, so it's going to have 3 dots. I want the single ones to face my other atoms, so I'm going to put a dot 1, 2, and 3. The dots facing the other atoms. Fluorine is in group 17, so it's going to have 7 dots. 1, 2, 3, 4. Back at the top is 5. I want my single electron facing the middle, so I'm going to go backwards. 6 and 7. On the right side, same thing. 1, 2, 3, 4. Top one's going to be 5, 6, 7. Bottom atom, I'm going to have 7 dots, so that's 1, 2, 3, 4. Single electrons here, so I'm going to go backwards. 5, 6, 7. Now I'm going to connect all of my single electrons. There are no lone pairs on boron, so this is another example of a non-polar atom. So we're going to call this one trigonal planar. This is the 3D structure of what a trigonal planar will look like. And again, there's no extra electrons on the center, so this is called non-polar. Next, we have NCl3. We have 1 N and 3 chlorines. So we're going to draw the nitrogen in the middle, and we're going to draw 3 chlorines around it. Nitrogen is in group 15, so it's going to have 5 dots. It's 1, 2, 3, 4, 5. Chlorine's in group 17, so it will have 7 dots. 1, 2, 3, 4, 5. Go backwards. 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Again, I want the single one facing the middle, so 7. Then we're going to connect the single dots. So this is what it's going to look like in the end. And now you can see that nitrogen does have a lone pair. So this is going to be an example of a polar molecule. So we call this one trigonal pyramidal. This is what the 3D structure will look like. Sometimes it will have the lone pair being shown, sometimes it will not. And again, since we have that lone pair, it is called polar. Our final example, CCl4. Here we have 1 carbon and 4 chlorines. So we're going to draw carbon in the middle, and we're going to draw 4 chlorines around it. Carbon is in group 14, so it has 4 valence electrons. 1, 2, 3, 4. Chlorine is in group 17, so it's going to have 7. 1, 2, 3, 4, 5. Going backwards, 6, 7. 1, 2, 3, 4, 5, 6. And I want the single one facing the middle, so 7. 1, 2, 3, 4, 5, 6, 7. And finally, the last one. 1, 2, 3, 4, 5. I don't want the fifth one here. 5, 6, 7. That way, all the single ones are facing the middle. And now we can connect those single dots. So this is what CCl4 will look like. We call this one a tetrahedral because there are 4 atoms connected to it. Since there's no lone pairs in the middle, we say that this one is nonpolar. Now we're going to talk about metallic bonds. A metallic bond is an attraction between a metal atom, only metal atoms, and a surrounding sea of electrons. So before covalent was dealing with all the orange elements, now metallic bonds are going to be dealing with all the blue elements. These are the metals, and they're usually on the left of the staircase. Remember, hydrogen is not a metal, so we're not going to classify it as one. So all of these in blue, those are metals. Those are going to be in the metallic bonds. The sea of electrons, you're going to see random electrons between the metal atoms, and they're going to be floating around. And that's what it will look like when the atoms are connected and you're going to see those electrons floating around. Metallic bonds are solid. Think about gold and silver. Those are always solid. They're ductile, meaning they can be drawn out into a thin wire. They have very high conductivity. That's why we use copper inside of wires so the electricity could flow through it. It's easy for us to charge our phones. And then it's malleable, meaning it's able to be hammered, flattened, or pressed permanently out of shape without breaking or cracking. So that is all for this part of the review over covalent and